Okay, so we have a table with A, B, C, D, E, and let's suppose that they are all keys, so there is no, all the attributes together make up a key. And suppose this table has the following multi-value dependencies. We have A goes to B, and B multi-value determines D. And like I mentioned, the key is the whole table. So there are no functional dependencies in this table. So obviously this table is not in fourth normal form because we have A multi-value determines B and B multi-value determines D, and neither A or B are the key. So they are non-trivial multi-value dependencies. So the idea is that you could pick up any multi-value dependency. So let's say we pick up this one and we say that, okay, this violates fourth normal form. So we start with that. So we have a table R1 with A and B. And then we have R2. So you bring the left-hand side of the MVD into R2. So we have A, C, D, and E. So if you look at R1, the key is AB, and A does multi-value determine B, but it's a trivial multi-value dependency. So out here, when you have, it's trivial. So it's in fourth normal form. So then the question is, you look at R2. So we know that the key for R2 is all of them. And, there's no B out here. So we do not have B multi-value determines. So if you look at it, you think, okay, there are no multi-value dependencies. But remember the rules that we did for multi-value dependencies in the last class. So that's the thing with MVDs, you kind of have to remember all those rules. Let me just bring up the last lecture. So these are the rules, I think. So this is the last lecture, and we have the transitive rule. If A multi-value determines B and B multi-value determines C, then A multi-value determines C. So keeping that in mind, if you go back here, so A goes to B, B goes to D. So that would imply that, so we have, so we get this from the transitive rule out here. So therefore, in this table, we have one multi-value dependency that is non-trivial. So you have to further divide this. So this is not in fourth normal form. So you divide that into table R3. And R4, which will be A, C, and E. Now these two tables are in fourth normal form because there are no non-trivial multi-value dependencies out here. So we get R and R1, R3, and R4 are in fourth normal form. So, so that's the technique to divide this table into 4 normal form table. So I'll do a couple of other examples just so that you kind of understand. So let's look at this next example. So we have this table R, A, B, C, D, and E. And we are given the following functional dependencies and multi-value dependencies. We are given AB goes to C, and ABC multi-value determines D. Okay, so so in this case, we have a functional dependency and a multi-value dependency. So therefore, I mean, if you look from the functional dependency, there's only one functional dependency, AB goes to C. So the key for this table is going to be A, B, D, and E. So the four of, so that's the key. So the idea is that, okay, so shall we go ahead and now, I think the easiest place to start with is the functional dependency. When you're dividing, I would say in general, just start with the functional dependency. So let's divide this table. So remember that when you say AB functionally determines C, it also means that it multi-value determines C. So it's from one of the rules. So anyway, so let's start dividing the table. So we have R1. So let's pick this one, that as the starting point. So we have R1, which is A, B, and C, where we have AB determines C. So, so the only functional dependency we have out here is AB goes to C. There's nothing else. So this is in fourth normal form. And then you have the second table, which is you bring A and B down, and then we have D and E. Okay, so so the idea is that, and so all of this is the key anyway. So we have that R1 is in fourth normal form. So the question is R2 in fourth normal form? Because it's the MVD is ABC goes to D, but here you don't have C. So if you look at it, it would say, you know what, there are no non-trivial multi-value dependencies out here. But that's one of the things I mentioned in the last class. Remember all those rules for MVDs. So let me just go back to the last lecture again. So we have this rule, that's rule number 8, which states that if you have functional dependency, AB goes to C, and then you have a multi-value dependency, ABC, multi-value determines D, then AB determines D, multi-value determines D. So therefore, if you go back, so we have this scenario in the example. So we have, so by rule 8 out here, we have AB multi-value determines D. So therefore, because of this rule, this table is not in fourth normal form. So I'll just put no, because we have A and B, multi-value determines D, and it's a non-trivial multi-value dependency. So we have to divide this table further. So we have R3, which would be an R4. So now all these are all in fourth normal form. So we have R is equal to R1, R3, and R4, and all of those are in fourth normal form. So, I would like you to try, I hope you understood this. So just try out this next one. We have this is actually I mean, I think that this is really, really simple. We have B goes to D and AB multi-value determines C. And I don't think there's anything that could be derived on this one. B multi-value determines D. Yeah, so I mean, this is a fairly easy one to break down. So we have the key is going to be A, C, and A, B, C is the key is A, B, C, and then you have R1. Let's bring B and D down. That's an easier one to bring down. And then you have R2, which is going to be A, B, and C, when all three are the key. And both of these are in fourth normal form. There's really nothing that goes through. So this is a pretty easy one, actually. So we have okay. So I hope you understood how to do fourth normal form decompositions. Are there any questions? And I mean, you could try this out. I'm not going to do this because this next example, I mean, you can work it out. And I put up a few on the assignment too. I mean, I haven't put it up formally. I just have put up in case you wanted to look at it to study for the quiz. So and I don't know if I put this question in the assignment, but if not, I mean, you could still try it anyway. Okay, so you can try this out, see if you can solve this. So this particular example, there are actually several ways of decomposing depending where you start. So it's really up to you which one you use. But one of the things you also have to look out here is that there are MVDs that you can derive out here. Because when you say, so for example, so remember, when you say A goes to B, that would imply that A multi-value determines B also. And then you have B multi-value determines C. So that would imply that A multi-value determines C. So that's one of the problems is actually you can get several MVDs for this particular relation because you can derive certain multi-value dependencies by using these three. So there's more than this. I mean, there are others too you could derive. So because of that, this particular problem has several ways of dividing. So actually, this is actually kind of a tricky assignment question or a quiz question because, you know, if I asked you to pick all, I mean, you might get 3 or 4, which are all correct in this case. So do you have any questions? Did you understand fourth normal form? Okay, so one of the things I mentioned when I moved from third normal form to Boyce-Codd normal form was that, you know, sometimes when you are a designer, you might choose to leave the table in a lower normal form. And for example, sometimes, typically people will divide it to either Boyce-Codd or fourth normal form. But the problem of dividing to Boyce-Codd or fourth normal form is that sometimes you lose functional dependencies. And I gave some examples of that in class when I moved from third normal form to Boyce-Codd. But let me just give you a small example out here. So there is a disadvantage of which is that you might lose functional dependencies. So for example, So let's look at this small table with 3 attributes A, B, and C, and you have the following functional dependencies. AB goes to C, and then you have C goes to B. Okay, so for this table, the attributes, the key is AB. Okay, but this, and out here, when you go C goes to B, this B is a prime attribute. So because of that, you could leave the table as this and as R ABC because it's in third normal form, but it's not in Boyce-Codd normal form. So, but because it's not in Boyce-Codd normal form, suppose you decide that, okay, because in Boyce-Codd normal form, the left-hand side must always be a key. On the other hand, in third normal form, either the left can be a key or the right could be a prime attribute. So if you decided to do a Boyce-Codd normal form decomposition of this table, you would get R1, which is C, B, and R2, which is A, C. Okay, so now we have these two tables, and both of these tables are in Boyce-Codd normal form. But the problem is you lost, that AB goes to C. So that's the reason that sometimes, when you design databases, you may choose to leave a table in third normal form. But like I mentioned, always at the very minimum, bring it to third normal form. Do not leave it in second normal form. So, so do you understand normalization? Do you have any questions? Because this was it on normalization. Okay, so then I'm going to move on to the next topic, which is data modeling. So one of the things I mentioned, I think, or in the last class, is that there will be only a total of 10 assignments. I want to try to finish the assignments by April. I don't want to give you any assignments in May because that's when all classes, you start getting a bunch of projects and stuff due. So the last assignment after MVDs is going to be on data modeling. So that doesn't mean I will be continuing to teach things like triggers and concurrency, all of which are very important topics. But all of those topics, the assignments are really labs because you don't really understand those topics unless you actually log in and try. So whatever I put up after that will not be graded. I mean, those are labs that you should try out and which I really recommend you try because you aren't going to figure out concurrency without trying out those things, or even triggers and constraints. You really have to see them in action. So I'm going to talk about data modeling, which in the new edition is chapter 3. And in the old edition, it's chapter 7. So they really kind of shuffle things around on the new edition. I mean, it's exactly the same material. I think they've kind of figured out that it was data modeling is a lot easier maybe to understand than maybe SQL. I don't know why, but I prefer to go start up with SQL, which I think is, I think that it kind of gives you a better understanding once you get into the data modeling if you really know SQL and understand the relational database. So I kind of disagree. I think I like the older layout better than the new layout. So, so data modeling is actually something that is done in the very early stages of database design. And I'm sure you've done in fact, I know you've done data modeling for, at the very minimum in your object-oriented programming class. And I think that it's also covered now in 519. So it's kind of covered in different classes, but I want to do data modeling from the relational database perspective. So like I mentioned, this is done in the early design phase. So it's extremely important because in the early design, if your design is poor, it trickles down. I mean, the impact of it is going to affect everything. If you have a poor design, that means your SQL queries will be much harder to write. So design really matters. So this is a very important part of databases. And usually design is done by most senior people. I mean, typically they won't get a person who goes out of college, just graduates, do design. I mean, it's a lot more difficult than just writing SQL queries. So this is the done. So this is the point at which the a designer kind of understands what are the functional dependencies in the organization that they are modeling. What are the attributes in a table? So stuff like that. So how does a designer determine FTs and the attributes in a table? So actually design this data modeling is done before normalization. Normalization really follows data modeling. So normalization, which we did, is also modeling, but it's the next step. So at this point, this is where at this time, this is, you have to talk to the end users, and that's the way you figure out. So you analyze. Trying to figure out the spelling of analyze. I'm not sure if it's a S or a, I think it's a Z. So analyze and evaluate systems. And this is largely done by speaking to end users. You speak to end users and you look at the existing system that they already have. Nowadays, I mean, everything is computerized. So when you're looking at existing system, when you're trying to design, you're looking at what they're doing in the company right now, why they want an upgrade. So this is that point of the study. And once you analyze, you kind of speak to end users and write down all the specification and stuff, then you make the conceptual design. So this is where you use UML diagrams. So here, I know you've done UML diagrams before. We are going to be using ER, entity relationship data models. So ER stands for entity relationships. So we have, and just like UML diagrams, the advantage of ER models is that it's all graphical. So it's easy for the end users to understand. So this is how it happens. You go speak to end users, you look at the existing system, and then based on your understanding, you create these ER diagrams, and then you show it to the end user. And usually it's something that even at this point, you typically involve someone at the organization end, someone who's kind of interacts, who knows a bit about computers and modeling. So you sit and interact and you kind of come up with this graphical system, which is easy for non-CS people to understand. So it's graphical. So it's easy for end users. Yet, that's the thing, even though it's easy for end users to understand, it is also formal enough and specific enough for the computer science designer, the person who's working on this end. So, okay, so let's look at ER models. So we have there are classes, and I'm going to relate it to the company database again. Okay, so we have, and these are the entities, which entities are really just tables. So objects with attributes. And then we have associations. These are also tables actually, so that's why in relational databases, everything becomes a table. So associations are relationships between entities. And that's the thing, associations are since everything in a relational database is a table, so even associations are really tables. So that's what they are. So, but I think a better way of saying is, remember that I did mention that for relational databases, everything is an interconnected table. So in some ways, associations are the interconnection between two tables. And I'll go to the company database and I'll explain. So it'll get clearer when I use the company database example. So first, let's start with the entities, the classes. So I'm going to first start up with this. And again, I'm going to use the relational database company. So we have so we look at the employee entity, because employee is the whole company database. One of the biggest entity out there is the employee entity. So we look at that. So we have so it's an object, and every employee out there has attributes. So let's look at an employee. So we'll say, so E1 is an employee, and E1, there are several attributes related to E1. So we have E1 has a name. So let's say his name is John. He has an address. He has an age, and so on, and phone number and all that. So that's like, so this is what you mean by an employee entity, is that employee entity has employees in it, and each employee has attributes. Oh, it's 10 o'clock. So I'm going to continue with this in the next class. So let me see. Yeah, so I'm just essentially going to just stay with data modeling on the next class. If you have any questions,